Hello, everybody. We've been talking lately about inference, and today we're going to build on what we've been talking about, essentially formalize some of what we've been talking about into what's traditionally called testing hypotheses. So we're going to talk about kind of how we approach that probability of being right, probability of being wrong. Are these two things the same? Are they different? That kind of thinking we're going to formalize and kind of think through what's good enough. So, just to review, what is inference all about? It's about drawing conclusions about data. Specifically, in fancy statistics language, it's about using data from a sample to generalize to a population. And it typically uses statistical analysis techniques to help make the guesses or inferences. Nobody likes this quote, but yet, right? How do we figure out who's going to win the race? Well, we're going to want to think about a track record. So what are we doing today? We're going to talk, right, to dig in to inference and make comparisons and spot variation and draw conclusions from our data. Let's start with a fun question. Is the winner actually stronger or faster than the losers? So what would you want to know if you wanted to know if the winner was stronger and faster than the losers? You'd probably want to know something about how much did they win by, right? On the left, that guy looks stronger and faster, right? He's winning by quite a bit. On the right, those horses, one of them's about to win by a nose. And yet, so what was the distance between the winners and losers? But you might also want to think about the winner's track record. I mean, Michael Phelps seems to often win by a fraction of a second, kind of like that nose to nose for the horse. And yet, if you win over and over and over again, even if it's only by a little bit, isn't that kind of sort of consistent pattern important too? That's what we're going to be talking about when we talk about, is the data good enough to convince us that two things are really different, right? That something is really better or worse? We would want to think, right, about how often it's better or worse, right? And how far removed it is. So let's think about some kinds of inferential questions. How likely are we to run out of additive if we buy 92 bottles a month? If new radios are twice as reliable as old radios, with what frequency can we expect different numbers of broken radios? How likely are we to go over budget if we budget a certain number of dollars? Would adopting a new accounting system improve our ability to pay our bills on time? Does organization A outperform organization B in some important respect? Does it take longer for us to repair planes in January than June? We ask all kinds of inferential questions. In fact, it's really what we want to do when we want to be making decisions from data. We ask inferential questions all over the Department of Defense and in our daily lives. And so if we want to do that, and we have data, we want to figure out if the data is feeding us some kind of fluke, or if one thing is really different from another. Is it faster, stronger, better, cheaper, more effective, more efficient, less painful, more popular, etc.? Or are those differences just the results of noise, or likely just the results of noise in the data? All right, so we're going to try to differentiate between meaningful differences and the noise that comes from data. To do that, we're going to test our hypothesis. So let's ask Julian. This is Julian, my son, several years ago. Julian, what's a hypothesis?
Hey Julian, what's a hypothesis?
Idea you can test.
As we all learned on Dinosaur Train. So while my then 3-year-old knew what a hypothesis was, hypothesis testing is hard. And this is because data is messy. Here's an example. My organization on average pays their bills in 28 days. I have data on a monthly average, 28 days. This month, bills took an average of 34 days to pay. Okay, what do I do about it? Do I panic? Do I decide it's time to start that reorg that will, get my name plaque on the wall? Because everybody loves a reorg. Reorg solve all the problems. Okay, what do I do? Seriously, right? This looks bad and we need to be paying things on time. And let's say on time is 30 days. An average of 34 days suggests that on average we're late instead of on average on time. And that's just not the kind of situation we want to find ourselves in, right? So on the one hand, we could panic. On the other, we could say, yeah, okay, 34 days happened, so what, right? It's probably just a fluke. Okay, the best way to figure out, is it just a fluke, right? Are you one of those people who sees the thing and you just assume it's a fluke? Or you assume you should panic, right? Rather than just sort of be who we are, let's go be data-driven people. Data-driven people should not make a decision based on this month it's 34, on average it's 28. Look, I'm data-driven and I panicked, right? That's not a data-driven decision. We should go and gather probably some more data. And we could find out, right, how far is that 34 from our monthly average. So let's go gather some more data about monthly data, about what's happening every month. We go and gather some historical data. All right, so that 28 looks pretty average and 34 looks pretty far away, right? Looking at historical data on what's happening every month, something weird appears to be happening this month to get an average like 34 when normally we're much closer to 28. But let's say, what if the data looked more like this when we went and gathered our data? Now that 34 looks weird, but it doesn't look anywhere near as weird as it did before, right? It's weird, it's a little bit out to the right, but things are pretty spread out in this data set. And that 34 falls well within the kind of realm of normal. All right, so how do we figure out if something's within the realm of normal or way out there and something to be concerned about? We're going to do it, right? We're going to essentially do what we've been doing by considering normal distributions and where things fall in our overall distribution of data. And to consider that, we're going to take a look at an example of a new training program. Let's see if it's better. So we have some data. Historically, our test scores have displayed an average of something like 19.5 and a standard deviation of something like 8. The average of the class averages is going to have, right, using the central limit theorem, the same mean, about 19.5, and we're going to use a smaller standard deviation called the standard error. It's going to take that population standard deviation 8 and divide it by the square root of n, which is going to be our sample size. So when we go and get a sample that we're going to try to see if it's different, we'll use the sample size we get from that to see how spread out we expect our data to really be. So then we're going to try to make a decision. This is the tough part, right? That data-driven decision. Is the new training method better? And should you implement the new training program? We're going to be essentially evaluating the claim that the new training program is better on average. Are some students going to perform better? Are some students going to do worse? Of course. But what we really want to see is, are things doing better on average? To see if things are truly better than the old program. Formally, so you've been doing this. We've essentially done this with several problems in class and in the inference labs that we've worked through. So you've seen this informally, but we typically put some kind of formal language on this. So we're going to test the hypothesis that the new training program is not really any different from the old training program. Essentially, the assumption we make is that the new training program is not really any different from the old training program. And therefore, that the average test scores you see with the new training program are distributed the same way as under the old program, right? So like this new average is just from the old population. And we typically put the burden of proof on the new program to prove that it's really better, really different than the old program. There's some funky language because, just like we love our Greek letters in statistics, we love some fancy terminology. So the first piece of fancy terminology is the null hypothesis. And this is the kind of assumption or that old idea that the new training program is not really any better from the old training program. I like the way a couple of textbooks I like describe this as the boring thing, right? Instead of the interesting finding, this is the boring finding. The boring finding is that the two things are the same, that we tried something new and it's not very interesting and it's not really any better. And so we make this assumption that they're the same, right? And what we're going to do with that assumption and with our null hypothesis is we will either fail to reject it or reject it. So we never, what we say, accept our null hypothesis, not the language we use. We use fail to reject or reject, right? So if we basically don't have sufficient evidence to reject our null hypothesis, we fail to reject it. And that's part of that burden of proof stuff. We never find someone innocent, right? We fail to find them guilty. And so even though it's entirely possible they're innocent, right, it works a lot like that, right? The burden of proof is on proving the test hypothesis, so we fail to reject or reject the null hypothesis. The test hypothesis, often denoted H1, is in this case, the new training program is better. In sort of fancy mathematical language, we're testing whether the average from the old training program is less than the average from the new training program. And here, we use less fancy language, we can either accept that or reject it. I like, as a picture, to think of it as, is it this, the picture on the left, that new training program is really from the old distribution? Or is it the picture on the right where the new training program essentially has its own distribution? So we get some data on our new training program. We get an average, 21.3, and we get the standard error, that population standard deviation of 8, divided by our new sample size of 30 for a standard error of 1.46. And we're going to see if we have compelling evidence that that old average is less than the new average. So we're going to go ahead and fill it in. We put our new average in here at x bar is 21.3. We use our normal distribution, and we see that there's roughly an 11% chance that the new average isn't really any different than our old average, right, using our normal distribution. Suppose there's a new and improved training program. Under our new and improved training program, we see an average test score of 23. Now do we think that there's evidence, right? You're winning by a little bit more here, right? So our new and improved training program, way out at 23, there's only a 0.8% chance that it's really part of that old statistical distribution. We need to decide what's good enough, what's enough likelihood that we're not wrong, that we should, right, accept our alternate hypothesis. Good form is that you set this level, what we call statistical significance, before you do your work, right? You decide what's good enough. And you should make this decision, right, based on the implications of being wrong. Typically, we set a level 10% chance of being wrong, 5% chance of being wrong, 1% chance of being wrong, something like that. With the new training program and a mean of 20 and an 11% chance of being wrong, we typically would fail to reject our null hypothesis. With the new and improved training program, where the test score was at 23 and only a 0.8% chance of being wrong, it's much more likely that we would reject our null hypothesis. There. The key thing we are looking at here is what we would call a p-value. The p-value is the probability of seeing the observed data given the null hypothesis. A low enough p-value says that the data we have observed would be very unlikely if our null hypothesis were true. Essentially, that means that you should, if you see a low p-value, you should reject the null hypothesis. When the p-value is high or simply not low enough, we say data are consistent with the model from the null hypothesis. We don't have enough reason to reject the null hypothesis. Formally, we say that we fail to reject the null hypothesis. Right? So that probability of being wrong, that's what we call the p-value. We set some kind of threshold for our p-value, and if our p-value falls below that point, we'll reject the null hypothesis, and we'll call the results statistically significant. The threshold is usually denoted as an alpha level, or A, so it's that 5%, 10%, 1%. We're going to call it alpha, the Greek letter, because we love Greek so much. You're supposed to select this alpha level before you look at your data, before you design your sort of analysis, right, and decide what a reasonable standard of evidence is based on, right, the overall question you're asking, not based on the data itself. Now, why don't we always require a super high burden of proof, a super high level of evidence? I think this has to do with that there are two ways of being wrong, and we have kind of a trade-off between the two. So let's think of, in our training program, the two ways of being wrong. Well, let's think of how we would be right. We're right if the new training is not better and we keep the old program, we're right. If the new training is better and we switch to the new training, we're right. But if we keep the old training and the new training is better, we're wrong. And if we switch to the new training, but it's not really better, we're wrong. So how do we make a decision? We don't want to switch and be wrong. We don't want to stay and be wrong. And part of how we make that decision has to do with the implications of our wrongness, right? In the case of the new training not being better and we keep the old program, it doesn't really cost us anything to implement it, and we don't really gain anything, right? So even if the new training is better and we keep the old program, right, nothing lost, nothing gained kind of thing. If we implement the new training program, it costs us about $10 million. If it wasn't any better, that $10 million is just a loss. If it was really better, it means we gained $10 million. But in some ways, failing to gain $10 million isn't always as bad as losing $10 million. It's part of why we put the burden of proof on the new thing, typically, to prove that it's better. We call rejecting our null hypothesis falsely, right, a type 1 error. So our null hypothesis was actually true, something we can't completely know, but we reject it. That can happen. We expect it to happen. If we set a significance level of 10%, we expect that to happen 10% of the time, that we'd get a type 1 error. We expect to get a type 1 error 5% of the time if we set, right, alpha at 5. We don't know how often we get type 2 errors, but there's a kind of trade-off that occurs there. So we can't set a level of our type 2 error, but we understand that we get more type 2 errors, right, the fewer type 1 errors, and vice versa, right? And those type 2 errors are where we fail to reject our null hypothesis, but the null hypothesis is false. We should make our decision about our significance level in part based on how dangerous or costly that type 1 error or type 2 error are. If making a type 1 error is especially dangerous or costly, so for things like new drugs, we often set these kinds of levels of significance, then we would set, right, a very small significance level, right? So type 1 error bad, tiny significance level. right? Or really big level of proof required. If a type 2 error is relatively more dangerous or costly, then we might choose a higher significance level. So something like this screening for cancer. We'd rather have some false positives, right? We'd rather have a few people get identified as, yeah, it looks like they have cancer, and then go and have to do more tests. If the cost of collecting data is small relative to the cost of a type 2 error, then it's probably a good strategy to collect more data, because then we can reduce our type 2 error while not affecting the type 1 error rate. Ultimately, this becomes a question of how much is enough. We're not able to eliminate all risks. We can't eliminate all type 1 and all type 2 error risk. And we need to establish an acceptable level of risk before running a hypothesis test. Often we do report multiple levels of significance. The result was significant at the 10% level, the 5% level, the 1% level, the 0.1% level to get around this issue. But essentially, we want to think about the implications, what's good enough, before we run the test, rather than be excited. Look, it was significant at the 10% level. Let's report it as significant because we can. Kind of poor practice. So we should make those decisions ahead of time, examine our evidence, and accept or reject our assumptions based on our level of acceptable risk. Now, a couple of things to talk about before we finish this conversation about statistical significance today. One that I think is particularly important is that statistical significance isn't the same as policy and practical importance. This is especially important if we're trying to make decisions from data. Maybe drug X is clearly better than drug Y, but does X represent enough improvement for us to care? This is notable and important when we're working with big data sets. Big data sets tend to make our standard errors very small and make even small differences statistically significant. The first time I worked with a 100,000 observation data set, I was shocked to see that everything I studied turned out significant at like the 1% level, but some of these things were meaningless differences, right? On average, someone had a 0.0001% higher AFQT score, and yeah, it was statistically significantly different, but who cares? Like that, one group had a 0.0001 percentage point different test score. So understand that when we do statistical significance testing, we're concluding whether a formal hypothesis test, whether we fail to reject or reject a null hypothesis. But it's not the end of the process. Don't make decisions entirely because of p-values. Business decisions should always take into consideration 3 things. The statistical significance of the test, absolutely. How likely is it you're rejecting H0 despite its being true? But also the costs of being wrong, the costs of both those type 1 and type 2 errors, and the effect size of the statistic they observed and how big is it, how meaningful is it in reality. So with that, I hope you're armed to make good decisions using data, not sort of blind decisions using data. Go forth and make good decisions. Finally, there are a couple of different kinds of tests that we can do. We can do one-tailed tests. These are kind of what we've been talking about. Is the new training program better than the old training program? Do larger contracts take longer to process than small contracts? Right? There's specific questions about the direction of the difference. Two-tailed tests simply ask, are 2 things different without any assumption of better or worse? So are 2 organizations different in the time it takes them to process bills? Do spring semester students perform differently than fall semester students? These are going to be a little bit different. Our alternate hypothesis, our test hypothesis, is going to be that these 2 things aren't equal, not that one is greater or less than the other. And we're going to consider the probability in both tails of the distributions. The kinds of confidence intervals you've been creating are essentially setting up 2-tailed tests. And computers typically do 2-tailed tests for us because they're not quite sure of what direction we would be assuming the test would be. With that, in a world full of uncertainty, we want to know, is program X better than program Y, worse than program Y, different than program Y, right? We need to have information in order to make decisions. And we go and we gather all these samples of data and do trials, do everybody's beloved pilot programs, and we get all of this data, and we need to try to make a decision from it. And when we can use statistics and quantify the strength of our evidence, right, it's a kind of signal to noise ratio that we get with this kind of formal hypothesis testing to try to inform our understanding of the risks that we're taking that are associated with our choices.